Okay, let me just see if I can flip it forward. All right, works perfect. So nice to meet everyone here. Thanks for the introduction. I'm Sasha. I have known James for a while on the biomass side, and I want to take a few minutes here and describe what anaerobic digestion is. I certainly don't know how well the room understands it, but I'll give you a bit of the global picture, and then we can talk a little bit as well about the more local Canadian market. So phrasing the problem first, the company Anaergia was developed around the concept of global warming, and of the 1.1 degrees Celsius that the humans have warmed Earth, about half a degree comes to methane emissions. And methane emissions are particularly problematic because they have a 84 times more or 85 times higher heat retention than does CO2. So it doesn't get a lot of attention, but the actual methane emissions are quite problematic. And where does methane emissions typically come from? Well, one place is landfills. And we now have fairly good technology which comes from satellites, and we can actually we can look down on these landfills, and we can watch what the methane emissions are leaking out of these stored waste facilities. And it's actually a Canadian technology as well. It's called I believe it's a GHG SAT or something along these lines. 41% comes from landfills and composting facilities. Another 26 can come from manure storage, and then a bunch of more can come from sewage plants and then leakage around oil and gas. So what we're looking to do as a company in general is take divert waste, create renewable natural gas, create clean water, and then as a byproduct as well, generate some organic fertilizer. Anaergia has a bunch of interesting technologies. We're fully vertically integrated from the pretreatment lines all the way down to the upgrading side of things, including some production of fertilizer products. But our real core technology is around the anaerobic digester. And now we'll get into just a more generalized. So that was the company pitch, but now let's talk about anaerobic digestion in general. So here's a general block flow diagram, we would call this. You can see some of the feedstocks, energy crops, plant byproducts, animal byproducts, bio-waste from households, industrial waste. Put it all into a tank that has no oxygen, and out of it you can get your renewable biogas. You can get electricity if you burn that biogas, and you can also get heat if you burn that biogas. And then we get this nice liquid called digestate, and that can be used as a fertilizer. Of course, now we all turn to AI for our answers, and if you ask AI how to describe anaerobic digestion to a fifth grader, it's a sentence that you see up there, but I see my face is cutting off at least a portion of it. So why anaerobic digestion? I do truly believe that it's the right solution within the value chain for waste, in organic waste. You get to take manures and agricultural residues like straw, stover, spoiled crops, and you can even purpose grow some secondary crops as well and turn it into renewable electricity. It's also nice because it's decentralized. Most cases you have anaerobic digesters either on farms or somewhere at a municipal wastewater treatment plant. So you're not creating the electricity all in one large mega plant. And then nutrient recovery, you can pull a lot of nitrogen, phosphorus, potassium out of anaerobic digestate material. And then from a society perspective, new jobs, green economy, and an overall reduction in the greenhouse gas emissions, like I mentioned. There's lots of talk out there about what's the best green fuel on the market. What we know is renewable natural gas is about the only carbon negative fuel on the planet, and it's hard to understand how burning a fossil or burning a gas can create a negative emission. The reason, if we go back to the first slide, comes from that methane has such a high global warming potential. Even burning that gas is better than letting it release to the environment. So we are taking food waste that would otherwise rot in a landfill, converting it into renewable natural gas, and offsetting a fossil gas. And unlike hydrogen, which can be considered another green alternative, it isn't very compatible with our existing infrastructure. So everybody has natural gas for the most part, at least in cities and industries. We have natural gas. Hydrogen is a little trickier. You can't transport it very easily. It doesn't behave very well within our natural gas grids, but we do have existing natural gas infrastructure. So a little bit about the technology side of things. Anaerobic digesters appear in a few different forms. This is a very typical type. You'll see these at a lot of wastewater treatment plants. You'll see them at most of the on-farm digesters across Canada and certainly elsewhere around the world. These are CSTRs, continuous stirred tank reactors. They are essentially a big tank. They form some kind of agitation. You add your feedstocks into them. You mix, biogas comes out, and then periodically you pull out the material, which we call the digestate. Another type is called a high solids plug flow digester. These ones are more like a highway. You add the material at one end of the digester, and they continuously move down the pathway all the way to the other end. You typically do have a mixer, but it's a much slower moving mixer inside of the digester. And this one helps to break down crust formation and pull material under the digester. There's also another type called garage style or batch dry fermentation. This is more typical in MSW, municipal solid waste. So where you would take kind of very crude, dirty looking material from municipal solid waste, you put it into these big garages, you close the door, and then you run them for a period of sometimes 10, sometimes 20 days. And then you open the door and you can remove the material out. Much more common in solid waste. And then lastly, the big dairy farms down in the US, the 10,000 cow dairies, they'll use more of these lagoon style. So lagoon style, very cheap, very simple. You don't use mixers, you don't use heating. So they tend to have very low volatile solids destruction, and they can be challenging to manage when they fill up with solids. So back to the feedstock side. So we know the digesters that we would be feeding around the world. These are generally the most typical feedstocks that you'll put into an anaerobic digestion facility. On the left, you have the lowest contamination, and then far on the right, you have the highest contamination. So your typical manures and harvested crops, they're actually the easiest because they're very pure. They don't contain very much contamination. And in general, they have a modest biomethane potential. As you kind of move along towards the right, you get commingled food and yard waste. This is kind of like your green bin material that you pick up if you're doing a very good job at source separating. And then you get into clean packaged food waste. This is like a grocery store or a cafeteria. And then you have contaminated SSO, which might come from a city collection, and then MSW, municipal solid waste. So when we talk about the Ontario side, maybe a large or a modest sized dairy of 500 herd, it might produce around 10,000 tons per year of manure. And this might produce about 170,000 cubic meters of RNG. What's really important for a lot of these on-farm digesters is the addition of external liquefied food waste. And the reason being is it generates about 5 times more biogas, even if you put in about the same quantity. It also brings in a considerable more amount of nitrogen, a lot of additional phosphorus, and those all can ultimately be returned nutrients to the soil. So it is quite important at these on-farm digesters that they do have the ability to bring in external feedstocks. Around the world, there's a bunch of different types of curbside collected source separated organics. This is one of the more abundant materials that needs to find a home. You have Italian SSO, which could have, considerable amount of packaging. Singaporean or Asian SSO tends to be wetter with a little bit less material. And then you get the American and Canadian, which tends to be quite dry and quite high in contamination. So all those materials, believe it or not, can produce a quite clean organic slurry that can be used within anaerobic digestion. Lots of technologies around the world. You can use pulping, which is almost like a big smoothie maker. You blend the whole material up and then scrape out the packaging. There's a lot of hammer mill technologies, and there's even some that you exert an enormous amount of pressure on it and you kind of squeeze out the organic material. So this is just a typical flow. So you'll bring in this source separated organics. It's collected from the green bins. You process it through some type of machine, in this case, for example, an Orex, where you're squeezing out a wet fraction or an organic material. Then you have to polish it. We use something called a hydrocyclone, typically to remove the glass and stone and grit. And then it goes into the anaerobic digestion, and it can create a clean digestate. So believe it or not, here's what it looks like. Good thing we didn't go before lunch. But there's a scoop or a bucket, tractor bucket load of what would be considered source separated organics. It has, let's call it somewhere between 20 and 30% contamination. And those go into pre-processing lines. And that pre-processing line spits out something that looks like that kind of minestrone soup or that oatmeal texture. And it has as low as 0.1% plastic and another, say, 0.3% contamination. So you can get quite clean, actually. And that material is very biodegradable, excellent biomethane potential. And because you're keeping it out of landfills and you're harnessing that methane, it's contributing quite dramatically to greenhouse gas emissions. So if you don't remove it, here's an example. A lot of material from the back end of anaerobic digestate will go to topsoil mixes. And here's just an example on if you haven't done a good job of removing those plastics. You can faintly see in that picture of the soil being removed, there's lots of what we call confetti, and that's the kind of plastic material that can accumulate. One of the main problems is when you go through the anaerobic digestion process, you do actually concentrate the plastic material. That's because the food waste decomposes, manure, straw, whatever it is, whatever you fed in, it decomposes, but the plastic stays in suspension. And so you can actually 5x increase that plastic concentration from what you feed to what you take out. But good digestate doesn't need to have plastic in it. Here's an example as well of a farm-based digester that's brought in organic, source separated organic material that's quite clean. And here is what the final product looks like. You can see on the plastic side of things, it's only around 0.16% plastic on a dry solids basis. And this material, it could be cleaned up further, of course. You'd love to see 0.0 there on the plastic, but it can be made like this and quite clean. Great source of potassium, also quite high in nitrogen. On the world scene, here is what we consider to be quality digestate, and it broadly varies by country and by region, but here is the kind of foreign debris and plastic contamination specifically. In Cal Recycle, for example, they consider foreign material greater than 4 millimeters. It's a bit arbitrary. You see in Ontario, it's 3. And you see in other places in Germany and Denmark, it's down to 2 millimeters. But the percentage is around, say, 0.5%, of which 20% can be plastic and varies by region. Whole goal being, let's, yes, get that material from going to landfill, get it beneficially reused, but let's not bring a bunch of problems with plastic to the farmland. I thought it was good to show what's happening in the world. So Europe has already proven biogas can scale. And in the graph, you can see since 2009, and that really doesn't even represent the start of the European biogas market. But since 2009, you can see the steady marching growth of the industry. Today, there's more than 20,000 biogas plants and biomethane plants across Europe. And the sector did experience a few booms from 2009 to 2014. This was incentivized by government, by the way, where the governments provided guaranteed feed-in tariffs for electrical production. And then there was followed by a steady growth right through to 2023, where the market continues to grow year over year. Its interesting fact is 6.7% of EU's total natural gas actually comes from biomethane. So this can make a considerable influence to the overall natural gas mix. Germany still remains the largest producer in Europe, and they generate about 100 terawatts of biogas and biomethane. That was in 2023. And that does demonstrate that once scale is achieved, you can actually do a considerable amount of improvement. The best country in terms of offset is Denmark. Currently, 37.5% of their overall natural gas comes from biomethane. It's a small country, but in the end, it's a pretty sizable amount of natural gas. Interesting for this group, for sure, is that the European biogas market was truly built with farmers. You can see in this curve, despite it being a little cut off by, again, my face, is 69% of European biomethane production is by agricultural materials. 6% much smaller sewage sludge, and then you start getting into some organic municipal waste, like I showed some images of the food waste, and as well industrial material. But certainly the dominant lion's share of production is coming from on-farm anaerobic digestion of residues, manures, etc. Some Europeans still believe that this market is going to continue to grow. And the reason for the multiple bars there is different agencies in Europe, the Gas for Climate, Eurogas, EC, CE Delft, anyways, bunch of organizations that try to predict the future. They all have obviously their own impressions of what the future will be, but in general, they all believe it's somewhere around a 39% CAGR, compounded annual growth rate, to 2030, and subsequently another 14% CAGR up to 2050. So the biogas market continues to grow, and one of the main drivers is taking themselves off of the natural gas source, from a lot of it coming from Russia, obviously. And that just further elaborates on this. Huge investment, $210 billion of investment will be needed to totally stop fossil fuels from Russia by 2027. And all of these goals are through the Repower EU, which is a response to the geopolitical conflict in Europe, aiming to get further action by 2030. So I thought I'd take you through some of these facilities, what they might look like. So here's a quite beautiful plant in Germany. You can see there's some broiler barns out the kind of the front of the photo here, and they're taking those materials and they're sending it directly into these anaerobic digestion facilities. Lots of labels there. I think what's critical is the tanks with the big domes on top of them are the actual anaerobic digestion systems. Some of them are also used for digestate storage. And then inside of the big building, that's where they're receiving a bunch of different feedstocks. So these are the kind of facilities that will bring in from neighboring farms. You know, you kind of co-op together. You have manure, straw, leftover maybe spoiled crops, etc. You bring it into the facility, you dump it in the reception hall, and then they use these big solid feeders to feed the material into the plant. And in the top of the picture, you can also see the silage clamps, and those are also where we have some purpose-grown crops as well. Europe was never shy about purpose-growing corn silage, even some hay and other grass crops, in an effort to feed these digesters. You can see here the kind of breakdown of material. So lots of chicken manure. In this case, it is liquid, 23,000 tons a year. There's cow manure, about the same amount, 20,000 tons a year. Pig manure, corn silage, 23,000 tons a year. And whole crop silage, 8,700. Now these vary day in or year by year, but in general, that's the kind of feedstock mix that a farm like this needs to bring in to make a plant like this work. This one is nearly a 1 megawatt electrical. It's about 750 Canadian homes worth of electrical requirement, but they also generate a huge amount of what's called renewable natural gas, about 5,000 Canadian homes of heating requirement being produced on this facility. And you can see the age, it's planning started in 2010 and it's still operational today. Here are some other just like snapshots of what these facilities look like. They do definitely have modern technology in them. Those are on the image of the box is actually on top of the digester. So you're standing on top of a digester. Below that is the liquid that's being mixed and fermented. And then those on the right are images of the pumping halls where you have big stainless steel pipes moving this material around throughout the facility. And here are some of the reception halls where you have solid feeders taking all of those feedstocks I mentioned, the solid manure, the corn silage, etc., and then distributing it into those anaerobic digesters to generate the biogas. Some other images here, the big engines, CHPs, combined heat and power units. That's what generates the electrical output and as well the heat that is needed for the facilities. And then in the image closest to me on the left is what's called a biogas upgrading system. So that actually removes the CO2 portion of biogas, generating that pure renewable natural gas. Some other facilities. This is one in Romania that we built going back, I think, about 15 years. It did slaughterhouse waste plus some wet commercial and some on-farm purpose-grown crops. 2.7 megawatts of electricity is the key takeaway. And here's sort of what some of these facilities look like on computer renderings. These were used obviously for the engineering phase of the project, not just models. You can see that one interesting thing is the red rings on the inside. That's like heating coils. So those are actually provided to keep the digester at a high temperature and allow those bugs that degrade the feedstocks to turn them into biogas. Here's another facility built just a couple of years ago. It's a modern manure management facility in Japan, Okayama biogas plant. This one's another one of those examples of aggregation. So you can see the tractor in sort of the center of the picture. It's arriving to the plant. It's bringing in dairy manure from around the neighborhood and the yards. It's going to drop it off inside of that reception hall with the solar panels on top. It may even fill back up with digestate and take it back to their farm. So you have that circularity. You give the manure, you return with digestate, and so you don't lose any of the nutrient units. What you're giving back is the renewable natural gas component. This plant was interesting because it was producing 1.2 megawatts of power, yes, electricity, but it was also taking the heat and a portion of the CO2 and taking it back to a greenhouse. So there's other kind of symbiotic relationships like that, where you can return the heat to greenhouses, return the CO2, and grow more crops. There's another quite large facility in Suarez, is what the name, it's 4.2 megawatts. We're starting to get into some quite large facilities, and this one's been operational for over 15 years. It's based in Hungary. And then Anaergia in general, we also do facilities at wastewater treatment plants. So this is a very good example of a modernized wastewater treatment plant. Obviously, your shower water, the toilet water, anything you flush down the drain basically ends up at one of these wastewater treatment plant facilities. We build these plants to incorporate the latest technology on the anaerobic digestion. This one is producing 3 megawatts of renewable electricity. It's combusting those in combined heat and power units, giving back the power needed to run the facility using the feedstock that comes in. So it's a nice circularity. And they also do something called co-digestion. So they bring in that liquefied organic waste, they digest it there on site, and then they can generate more power. And like you see there, generate about 2,000 tons per year of fertilizer. Another example of one of those quite large wastewater treatment plant facilities, this one is generating not electricity, but 320,000 MMBTU of renewable natural gas. Again, it's an example of sewage sludge co-digested with food waste, generating renewable natural gas. Okay, now we'll bring it back to Canada. There is, fortunately, quite a few biogas plants throughout Canada, and lion's share, 56% in Ontario. You can see the dots throughout the map. Some of those are on farm, Others are at municipal and manufacturing facilities. And then the red dots are landfill gas facilities. So that's where we take the naturally produced landfill gas, you pipe it out, you send it to an engine or an upgrader, and you, again, generate that biomethane potential. Here's the breakdown of what's out there. So 155 petajoules of biogas energy from RNG is realistically available, which would be the equivalent to about 3 million Canadian homes of consumption. And what we currently believe we're accessing is about 13% of that potential. And this doesn't even include if you were to do some purpose-grown biomasses or energy crops. Again, I hope I'm speaking to the right room in the sense that I'm saying that the majority of this is going to come from crop residues and those purpose-grown vehicles. There is still quite a bit of material or biogas in landfills that is not being tapped into yet, and livestock manure as well as, and also some urban organics. And even I was talking with Roger earlier, there's the pulp mill waste, about 3%. So very small, but there does exist that opportunity there. There's incentives coming. Canada's clean fuel regulation, which is called the CFR, have created an active compliance credit market for lower carbon fuels. What this essentially means is liquid fuels are being produced in Canada. They have a certain carbon intensity to them. The government recognizes this is detrimental. They would like those producers of those fuels to be doing what they can to lower the emissions. And so those firms can buy credits from companies that build and create renewable natural gas. And this can be a good market. Also, utilities, British Columbia, Quebec, and even Ontario, slowly coming around to it, are having their own incentives that are aiming to offset the natural gas grid. For example, in Fortis BC, they want to get 15% renewable gas. Quebec has a mandate of around 10% RNG by 2030. And Enbridge, I mean, they say net zero operations by 2050. So it's a little more vague. But then you see it right across the US as well. National Grid, SoCal Gas, Duke Energy, they all have some mandate to get themselves decarbonized, ideally by 2030, but others as late as 2050. Here's, I believe it's the last slide. This just goes over kind of what are those barriers. So it all sounds interesting, maybe not to everybody, but certainly there's a lot of what we see coming to our firms is a lot of people do find biogas is exciting, but they don't understand how they can implement it. There's obviously some risks like project financing, technology performance. That one, I think we're pretty much past that with 30 plus years of working facilities in Europe. There's some higher risk with municipal and provincial permitting. The pipeline connection is a big one. It's about $1 million a kilometer to get these things injecting into the grid, plus whatever grid entry unit you're going to be using. There's a high capital cost associated with these facilities as well. There is a net ROI, return on investment, but there is a high capital cost. You gotta be thinking of that. And then there is becoming feedstock competition. So those liquefied organic materials I was talking about, be great if those all made it to decentralized farms that want to build biogas plants. However, there is competition for those. And there really isn't defined policy yet in Ontario and Canada. Europe has done a much better job in my mind on this, and they have generated quite an impressive market for renewable natural gas. I think we're getting there though. We're starting to see the CFR program and others are building up and helping to support the market. Probably leave it there.